Welcome to this comprehensive educational video on understanding slope. Slope is one of the most fundamental and important concepts in algebra, and by the end of this series, you'll have a complete understanding of how to work with it in various situations. So what exactly is slope? Slope is a measure that describes two key characteristics of a line, its steepness and its direction. Think of it as a way to quantify how steep a hill is, or how quickly something is changing. The most common way to think about slope is as rise over run. This means we look at how much a line rises vertically compared to how much it runs horizontally. This simple concept is the foundation for understanding all slope calculations. Now, let me show you the mathematical formula for slope. When we have 2 points on a line, we can calculate the slope using this formula: m equals y2 minus y1 divided by x2 minus x1. The letter m represents slope, and this formula gives us a precise way to calculate it. Understanding slope is incredibly important because it appears everywhere in mathematics and the real world. You'll use slope to analyze graphs, solve equations, understand rates of change, and model real-world situations like the steepness of roads, the growth of populations, or changes in temperature over time. In this comprehensive video series, we'll explore slope from every angle. We'll start with the visual concept of rise over run, then learn how to find slope from graphs, tables, and coordinate points. We'll also cover the slope-intercept form and point-slope form of linear equations, and finish with exciting real-world applications that show how slope impacts our daily lives. Now that we understand what slope represents, let's define it more formally. Slope, often denoted by the letter m, is the ratio of the vertical change to the horizontal change between any 2 points on a line. We also call this rise over run. The rise is how much the line goes up or down vertically, and the run is how much it moves horizontally. Let me show you this visually on a coordinate plane. Let's start with a simple example. Here's a line that goes through 2 points. Watch as I show you how to identify the rise and the run. The rise is the vertical change from the first point to the second point. In this case, we go from -1 to +2, so the rise is 3 units upward. The run is the horizontal change from the first point to the second point. We move from -2 to +3, so the run is 5 units to the right. Therefore, the slope of this line is rise over run, which equals 3 over 5, or 0.6. Since this value is positive, we say this line has a positive slope. A positive slope means the line rises from left to right. As we move from left to right along the line, the y values increase. This creates an upward trend. Now let's look at a line with negative slope. Here's a line that falls from left to right. Notice how the rise is actually negative because we're going downward. The rise here is -3 because we go from +2 down to -1. The run is +5, moving from -1 to +4. So the slope is -3 over 5, which equals -0.6. This negative value tells us the line has a negative slope and falls from left to right. Let's also examine two special cases. A horizontal line has 0 slope because there's no vertical change. The rise is 0. No matter how far you move horizontally, the height stays the same. A vertical line has undefined slope because there's no horizontal change. The run is 0. Since we cannot divide by 0 in mathematics, we say the slope is undefined. To summarize, slope equals rise over run. Positive slopes rise from left to right, negative slopes fall from left to right, horizontal lines have 0 slope, and vertical lines have undefined slope. This fundamental concept will help us analyze and understand linear relationships in mathematics. Now that we understand slope as rise over run, let's learn how to find the slope directly from a graph. This visual method is one of the most intuitive ways to understand slope. When we have a line drawn on a coordinate plane, we can find its slope by following a systematic visual process. Let me show you the step-by-step method. Step 1, we start with a line on our coordinate plane. The first thing we need to do is identify 2 distinct points that lie exactly on this line. I'll choose these 2 points, -2, 0, and 2, 2. It's important to choose points where the line passes through exact grid intersections for easier calculation. Step 2, we identify the rise and run between these points. The rise is the vertical change, how much we go up or down. From our first point to our second point, we rise 2 units upward. The run is the horizontal change, how much we go left or right. From our first point to our second point, we run 4 units to the right. Step 3, we calculate the slope by dividing rise by run. 2 divided by 4 equals 1/2. So the slope of this line is 1/2. Alternatively, we can use the coordinate formula. The slope m equals y2 minus y1 divided by x2 minus x1. This gives us the same result but uses the exact coordinates. Now let's practice this method with 3 examples of increasing complexity. Example 1. Let's find the slope of this line. I'll draw a line that passes through some clear grid points. First, I'll identify 2 clear points on the line. I can see the line passes through 0, 1, and 3, 4. Next, I'll identify the rise and run. From 0, 1 to 3, 4, the rise is 3 units up and the run is 3 units right. The slope equals 3 divided by 3, which equals 1. This means for every 1 unit we move right, the line goes up 1 unit. We can verify this using the coordinate formula. 4 minus 1 over 3 minus 0 equals 3 over 3 equals 1. Perfect. Example 2. Now let's find the slope of a line that goes downward from left to right. This will give us a negative slope. I'll choose 2 points where the line intersects the grid clearly. -1, 3, and 2, -1. Now I'll find the rise and run. From -1, 3 to 2, -1, we go down 4 units, so the rise is -4. We go right 3 units, so the run is +3. The slope equals -4 divided by 3, which gives us -4/3. This negative slope tells us the line is decreasing as we move from left to right. Using the coordinate formula, -1 minus 3 over 2 minus -1 equals -4 over 3. Our answer is confirmed. Example 3. Let's tackle a more challenging line that doesn't pass through as many obvious grid points. This will test our ability to read coordinates carefully. I need to carefully identify 2 points on this steeper line. I can see it passes through -2, -2, and 1, 4. From -2, -2 to 1, 4, the rise is 6 units up and the run is 3 units right. Notice how much steeper this line is compared to our previous examples. The slope equals 6 divided by 3, which equals 2. This means for every 1 unit we move right, the line rises 2 units. This is a relatively steep positive slope. Let's verify. 4 minus -2 over 1 minus -2 equals 6 over 3 equals 2. Perfect. Remember that subtracting a negative number is the same as adding a positive number. Notice that this line with slope 2 is much steeper than our first example with slope 1. The larger the absolute value of the slope, the steeper the line appears. We've now mastered finding slope from graphs using both the visual rise over run method and the coordinate formula. These techniques work for any line, whether it has positive slope, negative slope, or is steep or gradual. When you have a table of x and y values, finding the slope is straightforward. You can select any 2 rows from the table and treat those x and y values as coordinate points. Here's a simple table with x and y values. To find the slope, we need to select any 2 rows and apply our slope formula. We use the same slope formula we've learned before. M equals y2 minus y1 divided by x2 minus x1. Let's select the first and third rows. The first row gives us the point 1, 3, and the third row gives us the point 3, 7. These become our coordinate points, 1, 3, and 3, 7. Now we substitute into our formula m equals 7 minus 3 divided by 3 minus 1, which equals 4 divided by 2, which equals 2. The slope is 2, but there's an important step we should always do. Verify that our slope is consistent by checking other pairs of points. Let's work through our first example with a straightforward linear table. Here's our table with x values from 0 to 4 and corresponding y values. We need to find the slope of this linear relationship. Let's select the first 2 rows, 0, 1, and 1, 4. We'll use these points to calculate our slope. Using our slope formula, we substitute m equals 4 minus 1 divided by 1 minus 0. This gives us 3 divided by 1, which equals 3. So our slope is 3. Now let's verify this slope by using a different pair of points, 2, 7, and 3, 10. Using points 2, 7, and 3, 10, m equals 10 minus 7 divided by 3 minus 2, which equals 3 divided by 1, which is 3. Perfect, our slope is consistent. Since we get the same slope of 3 from different pairs of points, we can confirm this table represents a linear relationship with slope 3. Our second example involves larger numbers, which requires more careful calculation, but follows the same process. This table has larger x and y values. Let's find the slope using the first and last points, 523 and 2083. Substituting into our formula, m equals 83 minus 23 divided by 20 minus 5. This gives us 60 divided by 15, which equals 4. Let's verify using the middle points, 1043 and 1563. Using 1043 and 1563, m equals 63 minus 43 divided by 15 minus 10, which equals 20 divided by 5, which is 4. Excellent, the slope is consistently 4. Both calculations give us a slope of 4, confirming our table represents a linear relationship. Our final example demonstrates why verification is crucial. Not all tables represent linear relationships. Here's a table that might look linear at first glance. Let's calculate the slope between the first 2 points. Using points 1, 2, and 2, 8, the slope is 6. But let's check if this is consistent with other pairs. Now let's check points 2, 8, and 3, 18. This gives us a slope of 10, which is different from our first calculation of 6. Let's try one more pair, 318 and 432. This gives us a slope of 14. We have 3 different slopes, 6, 10, and 14. Since the slopes are not consistent, this table does not represent a linear relationship. This is why verification is so important when finding slope from a table. Remember, when finding slope from a table, always verify your result by checking multiple pairs of points. If the slopes are consistent, you have a linear relationship. If they're different, the relationship is not linear. When you have 2 specific points on a line, finding the slope becomes a straightforward calculation using the slope formula. This is one of the most direct methods for determining slope. The slope formula is the foundation for finding slope from 2 points. Let me show you exactly how this works. Let me break down what each part of this formula means. The letter m represents the slope we want to find. The numerator, y2 minus y1, represents the change in the y-coordinates. This is the vertical change between our 2 points. The denominator, x2 minus x1, represents the change in the x-coordinates. This is the horizontal change between our 2 points. The key insight is that slope measures how much y changes for each unit change in x. By dividing the vertical change by the horizontal change, we get this rate. Now let's work through 3 examples to see exactly how this formula works in practice. Example 1. Find the slope of the line passing through points 1, 2, and 4, 8. First, let me identify which coordinates are x1, y1, x2, and y2. I'll use the first point as point 1 and the second point as point 2. Now I'll substitute these values into the slope formula. Let me write out the formula and then substitute each value. Substituting our values, y2 is 8, y1 is 2, x2 is 4, and x1 is 1. Now I'll simplify the numerator and denominator. 8 minus 2 equals 6, and 4 minus 1 equals 3. Finally, 6 divided by 3 equals 2, so the slope is 2. This positive slope of 2 means that for every 1 unit we move right, the line goes up 2 units. Example 2. Find the slope of the line passing through points 3, 7, and 6, 1. Again, I'll identify the coordinates. Point 1 is 3, 7, and point 2 is 6, 1. Substituting into the slope formula, y2 minus y1 over x2 minus x1. Notice that 1 minus 7 equals negative 6, and 6 minus 3 equals 3. Negative 6 divided by 3 equals negative 2, so the slope is negative 2. This negative slope means the line is decreasing. For every 1 unit we move right, the line goes down 2 units. Example 3. Find the slope of the line passing through points -2, -1, and 4, 5. This example includes negative coordinates, so I need to be extra careful with the signs. Point 1 is -2 minus 1, and point 2 is 4, 5. Substituting carefully into the formula. Remember that subtracting a negative number is the same as adding. 5 minus -1 becomes 5 plus 1, which equals 6. And 4 minus -2 becomes 4 plus 2, which equals 6. 6 divided by 6 equals 1, so the slope is 1. A slope of 1 means the line rises at a 45-degree angle. For every 1 unit right, the line goes up 1 unit. Let me summarize the key steps for finding slope from 2 points. First, identify your coordinates clearly. Second, substitute carefully into the formula, paying attention to negative signs. Third, simplify the arithmetic step by step. Remember, the slope formula works for any 2 points on a line. Whether the slope is positive, negative, or even zero, this method will always give you the correct answer. The slope-intercept form is one of the most useful ways to write a linear equation. This form makes it incredibly easy to identify key characteristics of a line just by looking at the equation. In this form, y equals m times x plus b, we have two crucial components. The letter m represents the slope of the line, which tells us how steep the line is and in which direction it goes. The letter b represents the y-intercept, which is the point where the line crosses the y-axis. This tells us the value of y when x equals 0. The beauty of slope-intercept form is that you can immediately read these values directly from the equation. No calculations needed. The slope and y-intercept are right there in front of you. Now let's practice identifying slopes and y-intercepts with 3 examples. Starting with a straightforward case. Example 1. Identify the slope and y-intercept from the equation y equals 2x plus 3. Comparing this to our standard form y equals mx plus b, we can see that m equals 2 and b equals 3. Therefore, the slope is 2, which means the line rises 2 units for every 1 unit it moves to the right. The y-intercept is 3, which means the line crosses the y-axis at the point 0, 3. Example 2 will be more challenging. We'll need to rearrange an equation to get it into slope-intercept form. Example 2. Convert the equation 2x plus y equals 5 to slope-intercept form, then identify the slope and y-intercept. To get this into slope-intercept form, we need to solve for y. We'll subtract 2x from both sides of the equation. Now we need to rearrange this to match the standard y equals mx plus b format. We'll rewrite it as y equals negative 2x plus 5. Perfect. Now we can easily identify our values. The slope m equals negative 2, and the y-intercept b equals 5. For our final example, we'll work with a real-world scenario and create a graph to visualize our slope-intercept form. Example 3. A phone plan costs $20 per month plus $0.10 per text message. Write this as a slope-intercept equation and identify the slope and y-intercept. The equation becomes y equals 0.10x plus 20, where 0.10 is the cost per text and 20 is the fixed monthly fee. The slope is 0.10, meaning each additional text message increases the cost by 10 cents. The y-intercept is 20, representing the base monthly fee even with 0 text messages. This demonstrates how slope-intercept form naturally appears in real-world situations. The slope represents the rate of change, while the y-intercept represents the starting value or fixed cost. Understanding slope-intercept form gives you immediate insight into any linear relationship. You can instantly see how fast something changes and where it starts. Point-slope form is another powerful way to write the equation of a line. This form is especially useful when you know a specific point on the line and the slope. The point-slope form is written as y minus y sub 1 equals m times the quantity x minus x sub 1. Here, m represents the slope, and x sub 1, y sub 1 represents any known point on the line. Let me break down each component. M is the slope of the line, and the coordinates x sub 1, y sub 1 represent a specific point that lies on the line. Point-slope form is most useful when you know a point on the line and the slope. This makes it perfect for many real-world applications where you have a starting point and a rate of change. For our first example, we need to find the equation of a line with slope 3 that passes through the point 2, 5. We're given that the slope m equals 3 and our known point x sub 1, y sub 1 is 2, 5. We start with the point-slope form formula. Now we substitute our values. The slope m is 3, x sub 1 is 2, and y sub 1 is 5. This gives us y minus 5 equals 3 times the quantity x minus 2. Next, we distribute the 3 on the right side. 3 times x gives us 3x, and 3 times negative 2 gives us negative 6. Finally, we add 5 to both sides to isolate y. This gives us our final answer, y equals 3x minus 1. For our second example, we have a fractional slope and negative coordinates. We need to find the equation of a line with slope negative 2/3 that passes through the point negative 4, 1. Our slope m is negative 2/3, and our known point is negative 4, 1. We start with the point-slope form. Substituting our values, we get y minus 1 equals negative 2/3 times the quantity x minus negative 4. Notice that x sub 1 is negative 4, so x minus negative 4 becomes x plus 4. Now we distribute negative 2/3. Negative 2/3 times x gives us negative 2/3 x, and negative 2/3 times 4 gives us negative 8/3. Adding 1 to both sides to isolate y, we need to convert 1 to thirds. 1 equals 3/3. Combining the fractions, negative 8/3 plus 3/3 equals negative 5/3. Our final answer is y equals negative 2/3 x minus 5/3. Our third example shows how point-slope form applies to real-world situations. A water tank contains 500 gallons at 2 p.m., and water drains at a rate of 25 gallons per hour. We need to find an equation relating the gallons remaining to the hours after 2 p.m. Let's analyze this problem. At time 0, which is 2 p.m., we have 500 gallons. The rate of change is negative 25 gallons per hour because water is draining. So our point is 0, 500, and our slope is negative 25. Using point-slope form with our point 0, 500, and slope negative 25. Substituting our values, y minus 500 equals negative 25 times the quantity x minus 0. Since x minus 0 is just x, we have y minus 500 equals negative 25x. Adding 500 to both sides gives us our final equation, y equals negative 25x plus 500. This tells us the gallons remaining after x hours. For example, after 10 hours, we would have negative 25 times 10 plus 500, which equals 250 gallons remaining. Point-slope form is a powerful tool for writing linear equations when you know a specific point and the slope. It's especially useful in real-world applications where you have a starting value and a rate of change. Remember that you can always convert between point-slope form and slope-intercept form as needed. Now that we've mastered finding slope from graphs, tables, and points, let's explore how this fundamental concept applies to real-world situations across different fields. Our first application comes from physics, where slope represents velocity, the rate of change of position over time. Consider a car traveling along a straight highway. We can track its position over time and create a distance-time graph to analyze its motion. Let's plot the car's journey. At time 0, the car is at the starting point. After 2 hours, it has traveled 80 miles. After 4 hours, it has traveled 160 miles. Now we can draw a line through these points and calculate the slope to find the car's velocity. The slope represents how fast the car is traveling. The slope of 40 tells us the car is traveling at a constant velocity of 40 miles per hour. This is how physicists use slope to analyze motion and calculate speeds. In engineering, slope is crucial for designing safe roads and ramps. Engineers use slope to calculate the grade or steepness of roadways. Consider designing a highway ramp that needs to rise 30 feet over a horizontal distance of 500 feet. We need to calculate the grade to ensure it meets safety standards. To find the grade, we calculate the slope and convert it to a percentage. This tells us how steep the ramp is relative to horizontal ground. A 6% grade means the road rises 6 feet for every 100 feet of horizontal distance. This is within safe limits for highway design, which typically allows grades up to 8%. In economics, slope represents rates of change, such as how production costs change with output levels. This helps businesses make important financial decisions. A manufacturing company tracks its production costs. When they produce 100 units, the total cost is $5,000. When they produce 300 units, the total cost is $9,000. By calculating the slope between these points, we can find the marginal cost, how much it costs to produce each additional unit. The slope of 20 tells us that each additional unit costs $20 to produce. This marginal cost information helps the company set prices and plan production levels. Throughout this video series, we've explored slope from multiple perspectives, as rise over run, from graphs and tables, using coordinate points, and in slope-intercept and point-slope forms. The slope formula m equals y2 minus y1 over x2 minus x1 is your universal tool for finding the rate of change between any 2 points. Understanding slope opens doors to advanced mathematics, including calculus, where slope becomes the foundation for derivatives and rates of change in complex functions. Thank you for joining me on this journey through slope. If this video helped you understand this fundamental concept, please give it a like and subscribe for more mathematics tutorials. Leave a comment if you have questions or suggestions for future topics. Keep practicing, and remember, mathematics is all around us, from the speed of your car to the design of the roads you travel on.